Hi, I am Eris Prisk, and this is my presentation on using deep learning to predict energy efficiency of buildings. So my problem statement is, can deep learning be used to predict energy efficiency of buildings? With rapid population growth around the globe, there's many practical issues regarding resources, one of which is energy. By better understanding the energy efficiency of buildings, we can create more sustainable buildings to help control energy resources. For my project, I chose to look at whether deep learning can be used to predict the energy efficiency of a building from the design specifications. This can help identify the most influential design parameters and therefore optimize the design process to create more energy efficient buildings. I ran this project locally on my Dell laptop with a 12th generation i7 processor, 16 gigabytes of RAM, and 10 cores using Jupyter Notebook. Multiple packages were imported, including TensorFlow for the modeling, Matplotlib and Seaborn for the visualizations, and NumPy, Pandas, and sklearn for the data manipulation. The data used was created artificially using a simulation program and made available on Kaggle. The data consisted of 8 input parameters and 2 output parameters, heating load and cooling load. There were 768 observations. Initial checks and data descriptions suggested orientation and glazing area distribution were both categorical variables, so this was explored further during the EDA. So I plotted the effect of each input parameter for each of the output variables. So relative compactness and surface area both showed a sudden change in trend at given points, and orientation showed very little effect on either load. I created a correlation matrix to show the relationship between the variables. This showed that the overall height and roof area were the most influential parameters. And as we saw in the previous graphs, orientation shows little correlation. So to pre-process the data, I decided to drop orientation because there were no signs of any correlation. The glazing area distribution was seen to have an effect. However, it's a categorical variable, so had to be one-hot encoded. The data was split into train and test data sets using an 80-20 split. And I used sklearn standard scaler to scale the input parameters to avoid the model being skewed by magnitude differences across the input parameters. The initial model was created using a single hidden layer with ReLU activation to allow for any nonlinear behavior. And then the output layer has a neuron for each output parameter, and I used linear activation due to the likely linear behavior in the model. Given the larger the building, the larger load should be expected to be required to heat or cool it. 30 epochs were selected, and Adam was chosen as the initial optimizer. MSE was selected as the loss function due to it being a regression problem, and the batch size was set to 1 to maximize the data given the small number of observations. To optimize the model, the number of neurons in the first hidden layer were analyzed using 3, 9, 15, and 21 neurons. All the models converged with a low MSE. However, 15 neurons gave the optimal value with an MSE of 5.088. Next, the optimizer was analyzed using Adam, SJD, AdaGrad, and RMS-Prop. AdaGrad struggled to converge. Note that these graphs I've shown here are the zoomed in ones. The notebook and report show the full convergence plots. Adam and SJD gave similar optimal loss values. However, Adam had a smoother convergence in addition to a more optimal loss of 5.962. The learning rate was then varied between 0.01, 0.005, 0.001, and 0.0005. The results all showed convergence at a low MSE with a learning rate of 0.01 giving the optimal value. Due to the bumpy convergence, I decided to use a learning rate of 0.001 as this only gave a small increase in MSE with a much smoother convergence. And the results suggest that further optimization may be possible with more epochs. So for the final model, I used 15 neurons in the first hidden layer with the Adam optimizer and a learning rate of 0.001. And the optimal MSE was 5.077 at 48 epochs. Ideally, I would have rerun the model with the 48 epochs for my predictions. However, due to the small change between 48 and 50, I just retained the model with 50 epochs for the validation. So generally, the model shows good prediction abilities. It shows better performance at predicting heating load than cooling load. Both of them show an increased delta to the true value as the load increases, but generally it shows very good predictions. So in summary, the model performs well at predicting heating and cooling loads, particularly at the lower load levels. And there's also plenty of scope to further optimize the model. For example, looking at would additional hidden layers be beneficial? Do we want to look into dropout? I didn't look into optimizing the activation functions for the different layers. There's plenty more hyperparameter tuning I could have done with the model. I also could have looked further at the glazing area distribution showed signs of it being a binary categorical variable rather than it's split into 6 different classes. So again, that could help get further performance out of the model. But the final model, I used the weights for that to do some feature importance, and that highlighted the key parameters which have the biggest influence on energy efficiency of buildings, which designers can then use that to focus on optimizing those to improve energy efficiency of buildings in the most streamlined way. And thank you for listening to my presentation.